Okay, so we're on page 27, and we're going to start with doing something with coloring to teach you something. Okay, so again on page 27, and so what we're going to do today is we're going to talk about your right to be able to take the claim that somebody said and reject it and say, hey, I don't think what you say is right. Like, I don't think there's really 20% blue M&Ms coming off the assembly line, or not being able to do that. Okay, so that starts with understanding a couple of things, and that's what we're going to begin with today. The first thing that we want to do is understand what this thing called a p-value is. So I have the definition. I also have a song of it, and then we're going to be drawing it. Okay, so here we go. First, let's actually draw it, and then we'll talk about the definition. So on this section, you have two little pieces here. We're going to draw two normal curves that are the same. So draw one right here, and then another one that's the same below it. Okay? So my blue color that I have here, my blue is just your regular old pen or pencil. Okay? And so then when I change colors, I'll tell you I'm changing colors and so on and so forth. All right. So what we want to first talk about is the fact that the null hypothesis is centered, okay? And of course that is the claim. You know, so for example, they'll claim that there's 20% blue M&Ms coming off the assembly line. Okay, so again, for each one of these things, we know that our null hypothesis is what is claimed. All right, so what I want to do also is I want to put an example of all of our little samples that we take. You remember when we did our M&Ms lab, you know, one person got 20% of their sample, had blue M&Ms, another one had a little less than 20%. Somebody had a little more than 20% blue M&Ms in their sample. And another one had less than 20% of their sample that was blue M&Ms, and so on. And so just put several p-hats in there. Just go ahead and take a little bit of time, put yourself 5 or 7 or so. Do that in both of these sets of data. Okay, because we got different samples. Now, while you're putting all your p-hats in there, I want to ask you this question. Why is everybody's sample not the same? Why do we have different amounts of blue from sample to sample? Sort of, yeah, kind of sort of ability. Okay, it's a sample, and I thought I heard something here. What did you say? Well, everybody's sample, is everybody's sample different from sample to sample? Okay, so you can follow that. Everybody has different samples from sample to sample. So what happens is this. We all have various p-hats values. Yes, we have various p-hat values because of this thing called sampling variability. Sampling variability means that you got a different result than I did because you got different data than me. Sampling variability happens because you got different data than me. Okay? So sampling variability is happening just because you happen to get something different. Now, it's reasonable to get something a little different. It's not okay to get something that is way too different. What is way too different in our normal model? Not just like 100 that way. Outliers. What would be considered an outlier? There you go. More than 2 standard deviations away. All right. So here's what's going to happen. Here's what's going to eventually happen. Listen up, guys. If you get a sample that's way out here that is, say, more than 2 standard deviations away, you're going to start questioning if this null hypothesis is actually in the correct place. Okay? Yeah, you're not sure if that claim is true. That's where we're headed with this. So let's now, I'm going to do a different color. I'm going to pick like purple. Okay? And so here is my sample results. I got this p-hat right here on this line. And then this sample on this line, and then this area that I shade here is the probability of getting this sample or something more extreme. More extreme in this case goes up. If I had a sample that was way down here to the left, which direction would be more extreme? If I had a sample down here to the left, which direction would be more extreme? Down here below. Okay, so a p-value is the probability of getting the sample that I got or something more extreme, getting this particular sample that I got or something more extreme if the null hypothesis is true. So if the data is really centered around the null hypothesis like you say it is, then the p-value, so let's say that that purple area is the p-value. And again, let's look at the definition up here. P-value is the probability of getting the sample that you got, that particular p-hat you got, or something more extreme if the null hypothesis is true. Okay, so that's the definition of what's going on here. And so I have a song for us to kind of help memorize that phrase or that definition. Okay, it's going to go to Brown-Eyed Girl. Do you remember when we used to sing, the p-value is the probability of getting this sample or something more extreme if the null is true. Okay, and then you're going to say it again. So this is something that you will be writing over and over and over again, pretty much word for word the definition of. So you're going to want to essentially have this definition memorized. So we're going to go over it a few times. So here we go.
The p-value is the probability of getting this sample or something more extreme if the null is true.
Okay, do it again. Get ready to start singing. You gotta know this definition. Here we go.
The p-value is the probability of getting this sample or something more extreme if the null is true.
Okay.
What do you mean?
We're not doing that one. We're not doing that one yet. Okay, so again, let me have you look at this picture as I'm doing. The p-value is the probability of getting this sample or something more extreme if the null is true. All right. So let's go ahead and draw a p-value on both. Well, actually, let's draw a p-value on both of these. I want to draw this other one a little bit bigger p-value. So I want a sample maybe further in and closer to the null hypothesis, okay? So draw yourself a sample that is further in and closer to the null hypothesis and shade that area. I am doing the same color as the p-value I did up above. So my p-value is the probability of getting that sample or something more extreme if the null is true. Okay, so now look at this sample that I drew in this second picture. Is it more like the null hypothesis or less like the null hypothesis than the one up above? This one down here, is it more or less like the null hypothesis? It's more like it. Why? Because it's closer to it. So this one is not a very unusual sample. This second one that I drew down here is not a very unusual sample because it's close to the null hypothesis. Okay, so again, here is our p-value, which is the probability dun, 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 of getting this sample or something more extreme if the null is true. All right, now the next thing that we want to talk about is where do these samples need to be in order to reject the null hypothesis? Because that's what we're wondering about. Can I reject what the M&M's company claims? So in a red color, I'm going to change to my other color. I'm going to talk to you about this thing called alpha. Kind of looks like one of the little ichthys fishes. Okay? Yep. So alpha is the size of the rejection region. No. Size of the rejection region. Actually, alpha does usually go in that direction because it is a lowercase Greek alpha, so it is in that direction. So there's alpha. So alpha is the size of the rejection region. And I will tell you, sometimes it is told to you. Sometimes you are told alpha. You are either given alpha, or if they do not give you alpha, then we default to 0.05, 5%. So that there's less than a 5% chance of having something happen, then our sample is in the rejection region. Okay? So the size of the rejection region is what alpha represents. And so you are either told that by the person who wrote the problem, or it is a default. Okay, so now let's put some alphas on here. I'm going to actually put it in the same location. Let's say here is the location of alpha. I'll go ahead and say it's 0.05. Okay, and we'll go ahead and put it in the same location on this bottom curve. There's my alpha, 0.05. Okay, here's what that means. This shaded area, and I'm just going to do like little stripes. This shaded area that I did with little stripes so I can still see the color behind it is 5% of the data. This shaded area here is 5% of the data. This area here that I'm doing striped is 5% of the data. Okay? So that is the size of the rejection region, and here's what's going to happen. If your sample is in the rejection region, then guess what you're going to do with the claimed null hypothesis? You're going to reject it. So look here at this first curve up above. Do you see where your your p hat is? Look at that p hat. Where is it located? It is in the rejection region. So we're going to write that out. So our p hat is in the rejection region. So if I get a sample out there, then guess what I'm going to do to M&M's company? I'm going to call them up and say, excuse me, I got a sample way out there that is so unusual to have gotten, I reject your claim. And I say that there really is not 20% blue M&Ms coming off the assembly line.
And then what do they do after that?
Well, and then they'll say, go take another sample and all. I mean, there's other things to be had, but it's not like you can sue them for them not, for false, yeah.
I reject it.
Right.
Do you like the M&Ms? Yes.
Okay. There you go. Okay. Let's look at this second picture. Look at this second picture. Look at where your sample is. Is this sample, this black p hat, located in the rejection region? No. So let me draw a picture to it and say this p hat is not in the rejection region. No. I mean, here, this red section is the rejection region, and that p hat's to the left, quite a bit to the left of it. Okay? So if I get one of those samples, it happened because of sampling variability, and it wasn't unusual enough to reject the null hypothesis. This p hat happened because of sampling variability, and it wasn't unusual enough for me to reject the null hypothesis. Okay, so let's summarize what we know here. We've talked about p-value. The p-value is the probability of doing what? Of getting this sample or something more extreme if the null is true. Okay, good. Let's listen to it one more time because you really do have to have this definition memorized. So here we go.
Oh no. I'm just gonna restart it.
Okay, here we go. Y'all got me singing.
Do you remember when we used to sing the p-value is the probability of getting this sample or something more extreme if the null is true?
Okay, good. Let's do it again. Here we go. Let me hear you singing.
The p-value is the probability of getting this sample or something more extreme if the null is true.
Okay, good. All right, so hopefully you are starting to have that definition memorized because we're pretty much going to be writing that over and over again. All right. Okay, so let's move on forward here to the next page. All right, here we go. Example 1. In 2001 National Vital Statistics report, it was indicated that about 3% of all births produce twins. I think we've seen this problem before, okay? But we're going to be discussing something different about it, okay? Data from a large city hospital found 7 sets of twins were born to 469 teenage girls. Running an appropriate hypothesis test, they got a p-value of 0.028. Explain what the p-value means in context. Okay, so this is what we're going to be learning, but we are first going to remember to write the parameter and the null hypothesis and the alternative. And so I'm going to actually use some of this space up here. P equals, what is this problem about? You remember doing this parameter stuff? P equals, not probability, proportion of what? Teenage pregnancies proportion of the teenage pregnancies that do what? Very good. That result in twins. And we're wondering, remember what we're wondering is if it's the same as all births. Are teenagers having births at or twins at a different rate than all people or all women or pregnancies? Okay, so what is our null hypothesis? HO colon P equals what? No. 3% of all births produce twins. So we're going to start out saying, oh, let's just say the teenage twin birth rate is the same as everything. And then we're going to wonder if we have evidence to say it's something else other than 3%. We're going to eventually wonder, can we reject that 3% claim or not? So did it say one way or the other, or is it a not equal to? Okay, I'm just going to go with not equal to since they didn't wonder about one direction or the other, greater than or less than. Okay. All right, so now here's the new thing. You've already done that stuff before. Here's the new thing. Here we go. We have a p-value of 0.028, and here's what that means. The p-value is the what? Okay, so there is a 2.8% chance, that's the probability of getting this sample or something more extreme. And instead of saying this sample, I'm going to put the sample results. What are the sample results that we got? No, the sample that they got was 7 sets of twins were born to 469 teenage girls. So there's the probability, that's a 2.8% chance of getting this sample. So I'm going to put those results, 7 out of 469 of getting this sample, sets of twins. Okay, so here's our song. The p-value is the probability, so that's our 2.8% chance, of getting this sample, that's 7 out of 469 sets of twins, or something more extreme, yes. And you can actually write that straight out like that. Or more extreme sets of twins, more or less, and that's kind of weird. More extreme sets of twins, and in this case, okay, if, okay, now what's the last part of the song? The p-value is the probability, good, 2.8% chance of getting this sample, 7 out of 469 sets of twins, or something more extreme, if the null is true, but we want to do that in context, if, in fact, what's the null hypothesis saying? What's the null hypothesis saying? Yes. I'll let you just write out the symbols there. If, in fact, p equals 0.03, because you've put a lot of other context in there. That's it. So that's the, is this even math? Yes. So this is a start. This is a beginning of a process. Okay? This is the beginning of a process. Okay, so let's practice that again. But what we're doing is we're going to add that to what you have already done in the past. So here we go. Okay, here's this problem. The packaging on a deck of random baseball cards states that the proportion of baseball cards in a package that are all-star players is 20%. The company plans to test this hypothesis to see if that approximation is valid. Due to contract agreements with the MLB players' unions, the company doesn't want there to be too few, but then also, does it say anything else? We don't want there to be too few, okay? A random package of 50 cards ends up having 6 all-star players in the package. Determine the p-value and interpret the meaning of the p-value. So, first, define the population parameter. What is this problem about? Proportion of what? So p equals proportion of, what is it? Proportion of the deck of cards? Oh yeah, gotcha. I like that. Nice. Look at how it says this. Proportion of baseball cards that are all-star players. Okay? Proportion of baseball cards in a package Okay, is that the correct denominator, by the way? Proportion of baseball cards in a deck that are all-star players. Okay, good?
That was good.
Okay? What's our null hypothesis? HO colon P equals 20%, so 0.20 or 0.2, whichever. However you like to do that. You can. You can. You can write 0.20, you can write 0.2, or you could write 20%. Those all things mean the same. Okay? What's our alternative? The MLB Players Union does not want there to be too few all-star players. So they are worried that there might be too few. Okay, so if it's not, I mean, do you have evidence that people are getting screwed over and not getting enough all-star players? Okay, so that's what we have to check and see. Are people getting, is there false advertising happening? Okay, all right, moving on. Let's compute a p-value. So do you remember this stuff here? Okay, what is the true p? What's the true p? The population p, which is the 0.20. What is our sample size? 50. So what is the where should all the samples center around? Good. All the samples should center around that same 0.2. Okay. How about this standard deviation thing? Do you remember that? Okay. It's p hat times 1 minus p hat. But it's p times 1 minus p over n. Okay, and I'll get you that number here in a second. How about p hat? What is our sample p hat results? I'm going to use this for a minute. Oh, where do I get that number? Ah, good. It comes from 6 over 50. So I'm thinking, though, that I just did this math, and I got 0.057. Okay? This sample results was stated to us up above to be 6 out of 50, which that decimal is 0.12. Okay, remember doing all of that stuff? Okay, so I need to get a p-value. A p-value is that thing that you did this. Remember when you used to end up this problem and you say the probability of getting this sample or something less than 0.2? Yeah, very good. This is the p-value. So what we used to have been finding was the p-value. I just never called it that. It was that probability. Okay, so what is our next step? Get a z-score. Very good. And remember, that's your p hat minus the p over the standard deviation of p hats. Okay, so that's our 0.12 minus the true p over the standard deviation of p hats. And that's negative 1.40. It didn't have anything behind it to round it. Okay? What do you have to say about that? Is that very unusual? How do you know? Is it more than 2 standard deviations below the mean? No, it's not. So it's not, in my mind, it's not too unusually low. So remember how I said earlier, okay, let's look at this. Remember how earlier in the class we were talking about a sample that's not too unusual? If a sample is not too unusual, am I going to end up rejecting the claim? Probably not. Okay, so keep that in mind. I'm probably not going to end up rejecting because it's probably not going to be in the rejection region, which that's future lessons that we're working towards. Okay, so what do I do from here on out to get that probability of getting that sample or something less?
Inverse norm of the area below.
Nope. I'm norm CDFing this from negative 99 up to negative 1.4, and that's how I'm getting that probability. Which is 0.081. All right. So all of that you've already done before, isn't that right? Okay. Now here comes the part that we just learned today. Interpret the p-value in context of this problem. This is your favorite part. So, come on, do you remember when we used to sing? Okay, so the p-value is the probability. Okay, so how do I want to write that probability? There is a what? 8.1% chance. Okay, so whenever it says p-value is the probability, we're going to say there's a such and such percent chance. Okay, so there is an 8.1% chance. That's the probability of getting this sample. What's the sample? Of getting what? What's our sample results? 6 out of 50 all-star players in a deck. All-star players, yes, thank you, in a package. All-star players in a package. Now, which way would be more extreme, by the way? Getting a bigger sample or a lower sample? What would be more extreme? How do you know lower? Yeah, nobody's going to complain if you get more players, but they're going to complain if you get less. It will always coincide with this. If we're worried about them being too small amount, then it's going to be that many, and more extreme is much less. So let's see. 8.1% chance of getting this sample all-star players in a package, or much less. Okay? If the null is true. So what do we say? And this one, you love me because I let you just go. If p equals what? No, 0.20. Oh, by the way, you know that if the null is true, you're saying this. This is what you get to write. If the null is true, that's what you get to put there if p equals 0.20. Okay, so that's what you get to put right down there. Is there another one that we get to practice of these? Okay, so then tomorrow you get to do like about 5 of them in class. And technically I'll probably do the first one with you tomorrow in class, and then you'll do the rest of the 4 more. So there's how that will work.